Hi everybody, welcome to the next lesson or pair of lessons in this series about your radioactivity and physics. So radioactivity in medicine, fascinating field. A-level has a whole unit on it, and if we've got a society using radioactivity in medicine is an important topic, and also I'm sure many of you may become medics in the future or working in that profession, so it might be useful for future, and also many opportunities for jobs in this field as well. So let's move on. Okay, in terms of objectives, what we're trying to achieve during this these two sessions is to evaluate the use of radiation applied internally and externally for treating tumours or for treating things generally. Explain the use of PET scanners, okay, there's nothing to do with cats and dogs, in diagnosis, and why isotopes used have to be produced nearby, half-life issue. And explain the use of radioactive tracers in diagnosis. Okay, so that's what we're trying to achieve by the end of this body of work. The two aspects of use for radioactivity in medicine: first of all, for imaging and diagnosis, i.e. finding out what's actually wrong with somebody, and then secondly, once you've used radiation for that, or you could have used radiation for that, then therapy, which is actually doing something about it. And you might well have heard of radiotherapy, people having radiotherapy, well, that's use of radiation, frequently nuclear radiation, for treating a condition in a patient. Okay, so this image here shows the location of a brain tumour. Now this was obtained by using physics methods with nuclear radiation, and it'll be treated with that as well. So we can see clearly this is a sort of slice through somebody's skull. Here's one hemisphere of the brain dividing down the centre, the other hemisphere, the left hemisphere, and then sadly this person's got a tumour within their brain. So we need to think about, and you can pause and think about it, or you can just do it in real time and think, right, how can we treat that without damaging healthy brain tissue? And it's clearly well embedded in the brain, so surgery may not be an option in terms of what's called invasive techniques. That means getting inside the body may not be an option, or may not be a safe option, and so therefore how might we do that? And then if we do use some sort of radiotherapy for this, then what may the side effects be? And we should know enough about radioactivity already to be able to come up with some decent ideas about what side effects might be of using radioactivity to treat conditions such as this brain tumour. Okay, so to emphasise the point that if we use radioactivity from outside the body, I mean, obviously the conditions inside, but if we use it from outside the body, we call it external radiotherapy, because the radioactivity is outside the body treating conditions within it. And this is a patient who you can see is about to undergo some radiotherapy, and they've got this metal helmet, I suppose, really shielding the top part of their head. They're held firmly and securely so they can't move, because obviously the patient needs to be still for the radiation to be applied. But this metal helmet's got holes in it, as you can see, a variety of different holes in it where beams of radiation can be aimed, and as we shall see, very precisely located and to treat the site of the tumour. And in this case, it's in this person's head. In diagrammatic form, we can see a similar thing. We've got the actual sources, in this case of gamma rays. We've got radioactive cobalt sources in all of these locations around the outside. It's a semicircle here, but it could be circular. And these gamma rays converge. But then what we saw in the previous slide, the spherical helmet that we saw that patient strapped within, is here, and what that does is that shields a large part of the brain, which means that radioactive sources, the gamma rays, can only reach quite narrow sections, and you've actually got quite targeted beams of gamma rays which you can aim at the target you're trying to treat. So rather than irradiating the whole head, the whole brain, which of course could have side effects and dangers, what's happening here is you actually use this method to limit and to target and to aim carefully where you're shooting the gamma rays at, in order to precisely hit the target, the tumour that you're actually aiming at. So that's a diagram for that one. To take that into the task there's going to be in a moment, if you consider the sort of circle of that, and we've got organs labelled on this person's body which are common sites where tumours may grow, and we can see that each of these alphabetically labelled points are potential gamma ray sources. So if you want to aim for a tumour in this part, let's say it's in the brain, then you'd use combinations of pairs of these gamma sources. Okay, so you'd use C and U, A and N, W and E, I and X, and the combination of where those beams of gamma rays meet, the major intensity of those is going to occur at this point here that is shown there. So that's where, if your tumour is there, you choose a particular combination of radioactive sources to actually target it there. Okay, some of it will pass through other parts of the body, but the highest intensity of nuclear radiation, gamma rays in this case, will be found at the site where you want it to be, this brain tumour. So we've seen a system of how radiotherapy from outside the body can be used to treat that. Okay, to work these out, take a ruler, decide where your tumour is, and use a ruler to join up sources that will meet and cross at that point. And what I've sent out with the materials for this lesson is a sheet on external radiotherapy, the diagram we've just seen, some introduction to it, some background to it, and then tasks which involve on this diagram here. Use the diagram to work out which organ is being treated for cancer. So using WK, UH, SF and BO, I joining them up, which organ is being treated for that. And there's a series of questions there which I'd like you to do on those to see if to work out which tumour is being treated by which combinations of gamma ray sources. So pause the video, get your sheet, draw on it perhaps different colours for different combinations for parts A, B, C, and then when you've done that, unpause the video and we'll go through the answers. Okay, you unpause the video, you've done the work I hope, and we're ready for the answers. So without further ado, we've done a worksheet, so just read the answers basically. So pause the video and check your answers with these. Note for 2A, B and C, these are the sort of main pairs that would actually cross in those places, but other answers are possible. And if the sources that you choose all cross on the relevant organ, then you've got it right. And the answer, the final one, is there. So check your answers against this, pause the video, and then pick it up again when you've checked your answers. If you're not sure about the answers, then wait till we do an office hours or tutorial session, and then bring them to that, and we can discuss it in detail in the future. Okay, moving on then. So that was external radiotherapy. Internal radiotherapy is where the radiation comes from within the body, or is placed within the body in order to have a therapeutic effect and treat tumours. You usually treat tumours and cancers within the body. Often it says in this case use a beta emitter, iodine 131. Iodine is a very useful radioactive isotope for use in the body. Placed within or very close to a tumour. It doesn't always require surgery, and a person can stay alone in the room while the source is in place. Okay, the radiographer might go out of the room, but in terms of what's happening here, the person can be alone with it. This example here is actually treating some sort of tumour within somebody's lung. Let's see the lung here. And what they managed to do is actually install a wire made of radioactivity. Okay, is inserted via the windpipe into the lung and close to the site where the tumour is, and obviously they've imaged that before so they know where it is, and they'll use that to actually the radiation of this to treat the cancer in that place, and they'll leave it there for a certain amount of time that they'll know and they'll have calculated, and then that will have an effect from the radiation here locally within that lung in this case, and it will kill some of the cancerous cells there, and it can be removed, and the patient can then come back another day, another week later or whatever, and have further doses of that. But it's quite localized, but it's happening within the body. The second part of this is something called brachytherapy, which is another type of treatment where tiny little seeds, and you might see them on this, and I've got a larger diagram, seeds, little tiny parts of radioactive material are actually implanted next to the tumour or within the tumour, and they're just left there to do their job. Okay, so this is called brachytherapy for this. It's implanting of radioactive seeds within this. If we expand the image there, you can see in white, these are the radioactive seeds, the radioactive isotope seeds within this. And you can see this is somebody's pelvis. Okay, you've got hip joints there, but this is somebody's pelvis here. So, perhaps this is cervical cancer. Perhaps I'm not a medical person, obviously, but again, these have been implanted within the body, so their radiation is very close to the site of the tumour, and they're left in there, and they have their effect. Obviously, we consider half-life for these as to how long we're going to leave them there, how long the half-life of the sources will be a measure of how much activity the person needs and how long that dose lasts for that one. Okay, so that's the internal radiotherapy using radioactive seeds within the body to treat as well. So another short task, and we've got our person here with their external radiotherapy and the person and the diagram there with the internal radiotherapy. So compare and contrast. That means in what ways are they similar and in what ways are they different. Pause the video and jot yourself down an answer to that question. Compare and contrast the treatment of tumours using internal and external radiotherapy. What have we learned so far? Pause the video, come back when you're ready. Okay, so, and the answers to those, hopefully you've written something along the lines of these. Hopefully I haven't just cheated and rolled it on, kept the video going, but hopefully you've actually had a go at this. That's where the learning is going to take place. Both treatment involves killing cancer cells in the tumours using radiation. Okay, as we know, radiation is dangerous, and therefore it can kill cells. Well, this time we want it to kill those cancerous cells. Internal radiotherapy, it's put inside the patient, usually a beta emitter. If you think of the properties that we understand, beta emitter will be good for those. And external gamma rays are used. And again, you might want to think about why we use gamma rays. The properties we understand from outside the body, remember, are directed at the tumour from outside the patient. And you should have filled in a worksheet on that as well. So if you've got answers that involve that, well done. If you haven't, rewind the video, have another look again, and make sure you can understand why those are the answers to this question. Isotopes was something we had right at the start of this unit, and isotopes are very important in the use of medicine. We're going to move on now to look at how the uses of PET scanners, positron emission tomography, to give it its full unabbreviated version, how we use those scanners in diagnosis, and why isotopes that we use in that process have to be produced nearby to where the diagnosis is happening and the imaging, and also explain the use of radioactive tracers in that diagnosis as well. So this is sort of a second little part of this topic, looking at PET scanners, and it's one of these things here where you've got a table with the patient on, and you've got some sort of imaging devices within there that the patient can be moved in and out of and used to image the patient. PET scans, positron emission tomography. You can see why they abbreviate it to PET, but tomography involves looking at something in slices. Okay, so we can't actually slice somebody open, but using imaging through different slices, we can then use computers to put that together and make 3D representations, can't we, if we look at slices. So the tomography slices, we use positrons that emit something and slices. And they're used in conjunction with tracers for diagnosis. Now, I've put these video links, which are about this, on the lesson support materials that you should have got through Frog. So again, have a look at those. This one only to 2 minutes 49, but this will give you sort of an introduction, some sort of animations about how PET scanners work, but we need to go through the theory of them now. Okay, so positron emission tomography. Okay, I've just said that, haven't I? Okay, tracers. Now tracers are radioisotopes. Okay, now we don't inject the radioisotope straight into somebody. That wouldn't do them any good at all. But the tracers are radioisotopes that are attached to other molecules that the body uses. Now, as we hopefully all know, the body uses glucose for energy. So if we can find a radioactive isotope that will attach to the structure of glucose, if you think about the complex structure of it and think about all the spheres added together in the structure of glucose. If we can actually add a radioactive isotope to that, then the body will absorb that, won't it? Because it uses glucose. And if there's a lot of cell division going on, because there's tumour, it will need a lot of glucose. So there'll be a lot of glucose there, a lot of radioactivity taken to the site of this tumour growth, and therefore we'll be able to see it because it'll be highlighted on analytical devices. So we inject the tracers, and they can either be injected into the body or breathed in. Okay, there's two ways of getting things into the body, either directly into the bloodstream or you can breathe them in some cases. They're absorbed into specific parts of the body, and we'll show you some examples of that later. And then they're detected with a PET scan. So the positron emission tomography is a scanner, it's a detector, but we use that in conjunction with tracers inside the body. Tracers need to have short half-lives, okay, and when you're thinking about what we're doing with them, injecting them or breathing them into the body, hopefully you can think, right, yeah, I now understand why things have to have short half-lives, and therefore these need to be produced very close to where the patient is. They've got a short half-life of in the order of minutes, then therefore, or tens of minutes, it's no good having to carry them from one side of the hospital to the other, because they'll have decayed away by the time they get to the patient. So we have to make some of these tracers very close to where the patient is actually located. In some cases, right next to the bedside, there are machines that can do that, and then short half-life, get used, and then they decay away, and the patient isn't exposed to too much radiation. So, on the textbook, page 217, but the tracer, okay, called positron emission tracer, positron emission tomography, the tracer that we use emits a positron. And that then interacts with an electron to release two gamma rays in opposite directions. There is a diagram coming. And that is what's known as annihilation, where matter meets antimatter. So again, some sort of quite advanced physics concepts here. And the gamma rays that are produced are detected by the PET scanner. Okay, so that's the fundamentals of what a PET scanner works with. We need a positron emitting tracer. Annihilation happens, and then the gamma rays produced as a result of that annihilation are then detected by the PET scanner. Annihilation, fantastic word to use, and spell, and therefore we need to understand that from a physics perspective. I know it's used in other contexts, but annihilation is a very specific physics term, and we need to know how it's used in medical imaging. So annihilation, great word. So what is annihilation? Well, it's when an electron and a positron interact and meet each other, basically, because an electron is a solid lump of matter, but a positron is actually an example of antimatter. Now, we don't get too carried away with that and get too in depth. This is GCSE after all, but that is what annihilation is. And I think I've got this diagram for you on the accompanying sheet that goes with this lesson. So they have opposite charges, so they attract each other, beta plus, beta minus, or an electron. They attract each other. When they collide, they're completely destroyed. And in their destroying, they have mass, don't they? You know that an electron's got a mass of approximately 1/2000th of an atomic mass unit. So these have both got mass. But when they annihilate each other, that mass is created and converted into energy, given by our friend Einstein's E equals mc squared. M, the mass of the particles, c squared, the speed of light, and the energy emitted is in the form of gamma rays. And those gamma rays formed by this annihilation move off completely opposite to each other, 180 degrees from each other, so they're given off in different directions like that. So that's what annihilation is. Marvellous. Okay, matter and antimatter meeting each other, and the gamma ray pair is given off perpendicular to the direction of the electrons in this one. Okay, so what for your own notes, you can pause this, I haven't put it on there, but you need to be able to explain what is electron-positron annihilation and how this can be used in diagnosis is what we're coming to next. So again, make your own notes, use the notes I've given you for that one, but be clear what it is. And it's the gamma ray pair that's really important here. That's what we use. We don't, annihilation just gives us the gamma rays, and it's the gamma rays that we want. This is a diagram from the textbook, and again, same idea. Annihilation and two gamma ray photons. A photon is a packet of energy given off in completely opposite directions, 180 degrees from each other. So how is that idea used? How do PET scans use that concept of annihilation? Well, we have radioisotopes injected into the blood as the tracer, which releases a positron. So the tracers need to be positron emitters. And it travels through the body tissue and eventually hits an electron. Of course, there are loads of electrons in the body. And when that happens, the gamma ray pair is produced and the mass is changed into energy. And that's gamma ray energy. So this energy equals gamma ray wavelength on the electromagnetic spectrum. And that's detected by sensors positioned around the patient, and that detection builds up a picture of internal organisms, one slice at a time. So if we look at the diagram here, we can see that the annihilation is happening close to the site of a tumour in the brain. The annihilation occurs, and then the photons are given out in different directions, in 180 degrees from each other. And if these are a series of detectors around the body, clearly they will pick up where this annihilation is coming from and give us one line and say, well, that annihilation is coming from somewhere between those two pairs of detectors, a bit like our external radiotherapy, but in reverse. Instead of targeting the radiation, we're seeing where it comes from. Another diagram of that hopefully illustrates that as well. We've got a ring of detectors around the body, and here's someone's skull lying down in the tunnel, so the sort of top of their head's facing us. These are their eye sockets, nose, nasal cavity. And if we have the positron electron annihilation occurring here, again, because we've perhaps attached it to glucose, perhaps a cell division here, so there's a lot of glucose here, there's a lot of annihilation happening, because a lot of positrons are annihilated with electrons here. And again, these pairs in opposite directions will be detected by 180 degree opposite pairs of detectors. And hopefully, as you can see from this one, as these go off in different directions, a computer can relatively easily decide, well, okay, where are these pairs, these simultaneous pairs of gamma rays coming from, and can actually then locate the source of the tumour. So positron emission tomography enables us to locate the sources of tumours through annihilation and detecting these gamma ray pairs which are coming from the site of a tumour. Okay, and there's the task on this at the end of this lesson. We can see PET scans here, two PET scans, a healthy brain on the left and the person on the right sadly has got Alzheimer's disease, and you can see that, you know, there's a great difference in the two. The radioactive isotope, the positron emitting isotope, has been attached to an element, a substance that is used by active brain cells. I wouldn't particularly know what that was, I'm not, a medical person, but you can see the same processes happen, but the Alzheimer's brain, you can see much less activity within it compared to someone's normal healthy active brain. And again, the question again, why do those isotopes that we use in tracers need to be produced near the patient? So again, I've mentioned that again, it's important. So that should be the end of part one of this lesson. There's been tasks to do, there's been things to have paused, so that should have taken you half an hour or so maybe. Textbook to look at, diagrams I've given out as well, and hopefully we've evaluated the use of radiation applied internally and externally for treating tumours. We've explained the use of PET scanners in diagnosis and why isotopes have to be produced nearby. We're going to go on in the second part of this, or lesson 2 I suppose, to look at the use of radioactive tracers in diagnosis. But for this video, that will be the end of where we are so far, and there will be a second part of this lesson looking at this in more detail and in the remaining stuff that we need to know. Okay, so I hope you find this useful. Watch the next instalment.